This guide will work through a simple example to demonstrate how the tool should be used and clarify the steps where user input is required. The Help tab provides useful background information. Details of the various stages. Definitions of land use types and criteria for determining soil drainage characteristics. A color coding is used throughout this calculator, whereby cells highlighted green require an action from the user, and cells highlighted yellow are calculated automatically. The River Camel catchment area is the zone in which new development may increase phosphate loading to the River Camel. The map is available on the Cornwall Council Interactive Map. The catchment area is accompanied by a map of the applicable wastewater treatment works. Developments that are located within the catchment area and will drain to a wastewater treatment works within the catchment will need to complete Stages 1 to 3 of the calculator. Developments that are located outside of the catchment area but will connect to a wastewater treatment works that drains to the catchment should not complete Stages 2 and 3. This may be applicable to certain developments in Bodmin, Delabole and St. Mabin. Alternatively, where a site is located within the hydrological catchment, but drains to a WWTWs outside of the catchment, for example Luxillian and Wadebridge, then Stage 1 should be set so that the occupancy rate is 0. The Info tab allows the user to input information relevant to their development, such as the address and details of proposed works. Stage 1 calculates the additional phosphate added into the system as a result of an increased population. The first step is to calculate the additional population. Here the user should input the number of dwellings proposed. This will be multiplied by the national average occupancy to calculate the increased population. For a proposed development that already has a population, only the additional population should be inputted. The second step is for the user to select if the sewage is to be treated by wastewater treatment works or by on-site packaged treatment plants. First I will run through the wastewater treatment works. The user should ensure that Yes is selected for wastewater treatment works and No is selected for packaged treatment plants. You cannot select both options. The user must then select the wastewater treatment works that the development will connect to. If this has not been determined, then the user should select the closest works to their site. If this is still uncertain, then there is the option to select Unknown. This will automatically calculate the phosphate loading to the system in kilogram per year. In the case of packaged treatment plants, the user should answer Yes and ensure wastewater treatment works are set to No. The user should then input the phosphate reduction efficiency of the packaged treatment plant that is to be installed. This should be based on published results from the manufacturer that calculated the value from laboratory test results or effluent concentrations from real-world applications. If the efficiency is unknown, then a precautionary value of 50% can be used. To achieve the highest reduction values, then packaged treatment plants with specific phosphate stripping should be used. Step 3 presents the total phosphate load resulting from the additional population. Stage 2 calculates the phosphate loading from the existing site land use. Firstly, the user must determine the dominant soil type of the site and should refer back to the Help tab. The dominant soil type for a site can be retrieved from Soilscapes. By clicking on the soil underlying the site, the user can identify the name and number. The user should look to see if their dominant drainage type falls under free draining or impermeable from the table shown on screen. The majority of soils in the region are freely draining. In the case where free draining and impermeable soils are both found on site, then the soil type with the largest area should be chosen. The user should then answer yes if the soil is free draining. or no if it is impermeable. If the drainage is impermeable, then there is the option to select if drainage systems are installed on any managed grassland fields, as well as arable fields. Next, the user should input the various current land uses on site in hectares. Multiple land uses can be selected and the total area automatically calculated. This will automatically calculate the total phosphate loading from the current land uses. Stage 3 calculates the phosphate loading from the proposed land use. The user should input the proposed land uses of the site, ensuring the total area matches what was inputted in Stage 2. If large-scale designed wetlands are to be used, the user should input the predicted phosphate banking value in Step 3. Step 4 calculates the total phosphate load from the proposed land use. Step 5 provides the gross phosphate loading and should be used as a guide when iteratively adding on-site mitigation, which will be discussed later. Stage 4 provides an overview of the previous 3 stages and calculates the total phosphate load by adding the phosphate from the additional population to the net change in land use types and applying a 20% buffer. The stage considers the loading under current permit limits and AMP7 future permit limits. Step 5 tells the user if the project is phosphate neutral. If the project will generate additional phosphate, then mitigation is required. The user should progress to Stage 5. Stage 5 provides guidance on the mitigation required, either off-site or on-site, and how this can be offset through changing land uses. Step 1 outlines the excess phosphate that needs to be offset for the project to be phosphate neutral. Step 2 allows the users to select either on-site mitigation or off-site mitigation. Again, the user should select yes or no as appropriate and select either on-site or off-site mitigation, not both. Taking the example of on-site mitigation, the user should select the land use of the mitigation site, which in this case will be a part of their site. If the exact location on site where mitigation will be situated is unknown, then an average value can be used. For off-site mitigation, the process is very similar. The user should select yes and select the drainage type of the mitigation land use. The user should then identify what the land use is of the off-site mitigation area. If more than one land use is selected, then the average runoff coefficients will be automatically used. Step 3 provides an indication of the area needed to be created for each mitigation land use, assuming that only one mitigation land use is used. Step 4 allows the user to input the amount of phosphate they wish to offset for each mitigation land use type, and the area needed will be automatically calculated. In the case of wetland, the user should input a bespoke banking coefficient and select the amount of phosphate to be offset. Step 5 works the opposite way to Step 4, allowing the user to input the area of the mitigation land use type, and the tool calculates the phosphate that would be mitigated. The values outputted will give a good guide to the areas needing to be mitigated for off-site mitigation. However, in the case of on-site mitigation, the actual area of mitigation needed will be slightly less than what is calculated in Stage 5 due to relative changes with the other land use. Therefore, the user should input the mitigation land use areas given in Stage 5 into the Stage 3 and iteratively alter the areas until the proposed development is phosphate neutral. Stage 6 acts the same as Stage 5, but the total phosphate to be mitigated is for AMP7 permit limits. Where package treatment plants are used, or there is no difference between the permit limits, then there is no need to go any further than Stage 5. Stage 7 demonstrates the difference in the areas between the current permit limits and AMP7 limits.